the point. They're talking about adding energy to the atmosphere. They're talking about the temperature going up. But they're ignoring the basic tenet of why we use hydrocarbon fuels. It's their energy density. A single kilogram of coal, which has 27 million joules of energy. It takes 1,000 joules of energy to heat 1 kilogram of air by 1 degree Celsius. So you divide 27 million by 1,000, you get 27,000 kilograms of air heated by 1 kilogram of coal to 1 degree Celsius. Now, if you're like me and have a penchant for doing chemistry in your head, you divide the mass of the combustion products of CO2, which is 3 kilograms of CO2 by the 27 kilograms of air, and you come out with a number. It's like 100 parts per million of CO2 would be added to that 27,000 kilograms of air that you had, that you started off with. Why didn't anybody even think to do any of these calculations before they started making when they were doing the correlation? There is a direct correlation between the production of CO2 and the heating of the atmosphere. There's no ifs, ands, and buts about it. It's just that they made the wrong connection. And because they made the wrong connection, they're trying to get us to do the wrong things. For oil, the numbers are even more astounding. A single kilogram of oil, when it's burned, will produce 3.15 kilograms of CO2. And it heats 47,000 kilograms of air. Now you divide 3.15 by 47,000, that comes out to 67 parts per million. Now, we've added about 150 parts per million of CO2 to the atmosphere from combustion processes. So, you have to figure that the temperature rise from that should have been higher than 3/4 of a degree, because I just pointed out that the parts per million are greater than what would have been added if you heated it by 1 degree. So, doing some calculations on supposition of how much came from coal and how much came from oil, I chose a nice round figure. I said coal's been burned since 1800. Oil hasn't been used that much since, but it was discovered and was being used in various quantities, but really took off in the 20th century. So I assigned it 20% value, and I took coal as 80% value. And when I did the calculations and based on the energies released from the combustion process, I came out with a temperature rise of 1.68 degrees Celsius, which is twice what the IPCC says. And those are just the basic facts of this. If there is a greenhouse effect, that the fact that the CO2 that's in the atmosphere is absorbing more IR and adding heat to the atmosphere, it should be additive to the combustion energy that's added as well. So the temperature shouldn't be just 1.68. It should be 1.68 plus 0.78, which is over 2.5 or 2.4 degrees, close enough, degrees Celsius. But the IPCC says it's 0.78. So there's something terribly wrong with the way they're doing their calculations. I have had arguments with climatologists who dismiss it. They take the idea that they can do these calculations, and they send them back to me. A professor from U of T, who shall remain nameless, sent me back his calculations about my energy stuff, and I looked at it and I said, that's pretty low, 0.008 degrees per century. And I looked at his calculations and I thought, oh, that's what he did. He used 47,000 joules 47 kilojoules instead of 47 million joules. He was off by a factor of 1,000. So I politely sent him back my correction, asked him to verify his numbers. He said, "You're right, I made a mistake. I'll have to think about it and get back to you." This was last November. He's still thinking, and I'm still waiting to hear from him. I've been sending him emails from time to time, but no response. That's the way life is when you're dealing with people who you catch making a big mistake, and then they have to admit it, and then they have to think about it. And they really have a hard time thinking about it, especially if it destroys their paradigm that they've been brought up to believe and worship. So that's part of the problem. Now, the issue that some people have tried to use with me about this thermal heating is that, the thermal heating from combustion would radiate away, and that we can dismiss it because of that. But the thermal energy from CO2 stays. Well, that doesn't make sense, because thermal energy is kinetic energy. If you've got kinetic energy from one source, it should be additive to the kinetic energy from another source. And if it's not, you're doing something really, really wrong. And that's part and parcel of the whole issue with this greenhouse effect and global warming. Not that there's no global warming. Oh, there is, for sure. It's just that it's not attributable to this greenhouse effect. And that's the issue that I have the biggest problem with. I estimated the heating effect of an asphalt road. You know asphalt? Nice and black. Black absorbs 100% of the sunlight. 100% of the sunlight is 1.3 kilowatts, or 1.3 kilowatts per square meter continuously during sunlight. You take the area, multiply it by the time, and by the 1,300 watts an hour is 1,300 joules per second times 3,600 seconds. So it's roughly 5 megajoules per hour per square meter. And you get 100,000 of those, that's 100,000 square kilometers. That's an awful lot of extra heating. That should also be additive to the thermal heating and to the IR, radiation greenhouse effect, if there's any. So there should be a temperature rise over the past 200 years of something in the order of about 5 degrees Celsius, as opposed to the 0.78 that's been claimed by the IPCC. And if we're going to believe that there is a heating effect, then we have to understand that these heating effects have got to be additive and be understood to be additive because the science says they should be. Not because I'm saying they should be, but that's the way the science is. Sorry, I misquoted. The cumulative total should be 4.14 degrees Celsius for all of them. Now, some of my other favorite topics. Biofuels, renewables. Renewables, we've been told that we should be using renewable energy sources because they're better for the environment. Well, if that were the case, I would agree with it. But that's not the case. When you use a kilogram of biodiesel to power your diesel-powered vehicle, whether it's a train or a plane or an automobile, you still put out the same amount of energy into the atmosphere as you do if it's a kilogram of petrodiesel. In fact, you put out a little less, but you're a little less efficient, so you have to use more biodiesel. You add more CO2, but CO2 isn't the problem. It's the energy. And the energy is the problem that we have to come to grips with and face, because if we don't, we're going to end up continuing to do these things that make sense to somebody but don't make sense to science. And so we end up doing the wrong things. Now, alcohol, ethanol, is another biofuel, and you can burn it directly. You can use it to make biodiesel. You can do various and sundry things with it. But if you're growing grain to make biodiesel, whether it's alcohol-based or whether it's oilseed based, that doesn't make sense, because you're taking a food source and turning it into a fuel. It's better to make biodiesel from waste products that are, use deep fryer oil from restaurants, things like that. Fermenting waste carbohydrate products that are collected by the city, things like that, where we can actually get a secondary use of the product as we're using it. And that's an issue that I feel strongly about. There's no point in growing, hundreds or thousands of acres of oilseed crops just to turn it into biodiesel, so we can say, oh, I'm using biodiesel in my car, so I can drive it anywhere and do anything, and it's not going to affect the atmosphere. Well, that's a crock. And it needs to be pointed out that it is a crock, because if people don't understand this, they will continue to do the wrong things. In the name of saving the planet, we actually make it worse, because everybody thinks they're doing the right things. The only thing that makes sense is wind power. Now, wind power cools the atmosphere. When you take energy out of the wind gets colder. You turn it into electricity. The electricity gets used, it goes back into the atmosphere. But because there's no such thing as perpetual motion, you can't put as much energy back in as you took out. So you're actually net cooling the atmosphere every time you use wind power, which is not very much, but it's enough that it would be a great way of cooling our planet if we could get more wind machines, wind-powered generators available for general electricity production. The problem with wind is, as you know, it's not always windy, except in some places, like Parliament Hill. But that's a different story, and I'm not going to bother going there. I pointed out that the energy that we use has to go somewhere. Once it's created, once it's released, it has to go somewhere. And the easiest place for it to go is in the atmosphere, because everything is air-cooled. Ultimately, when you slam on the brakes in your car, you scrape the pavement, your brakes get really hot, and those brakes get air-cooled eventually. The next morning, your brakes are back to ambient temperature. The same for streetcars. Streetcars weigh 25 tons. Every time you've got a streetcar stopping and starting, it has to slow down. It has to take the heat from the kinetic energy from the motion and put it into heating the brakes. And eventually the brakes cool by being air circulating over. So it heats the atmosphere. So people that think streetcars are great, they don't understand the science of how streetcars operate. And there's issues with that as well. I'll be talking about streetcars at my next lecture on October the 8th. CANDU reactors are good because they only produce about 20% electricity out of their nuclear reactions. But the 80% of waste heat goes into the ocean, because you use cooling water at Pickering, Bruce, to cool these massive generators. That heats up the water a little bit. It eventually flows downriver to the oceans, and the oceans warm up a little bit. Now, the good thing about the oceans are that they're The mass of the ocean is 270 times the mass of the atmosphere.